Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is computer memory system. Please follow me in this engineering lecture series by subscribing to my YouTube channel at https://youtube.com/@Ndinechi C. Like, share, and drop your comments in the comment section or reach out to me using my email address. You can listen to my introductory lecture on computers in Module 006 using that link. You can also listen to other lectures on computers already done by me in Module 014 using that link. More importantly, you can also listen to my lecture on computer number systems in Module 019. They are all very useful to help you to understand better this particular edition of our lecture, which we term computer memory systems. Now, the memory of a computer is used to hold two distinct types of information. The first is the data, which is to be processed by the computing machine, and the second is the finite sequence of operations, which will process that data to produce the desired result. This finite sequence of operation is called the algorithm or instructions. Normally, algorithms operate on a data structure. It is important to note here that the data structure is a description of the form of data rather than the particular data values. The memory of a computer is usually divided into many similar cells, also known as locations, which can be individually addressable. This means that the central processing unit, the CPU, can uniquely identify a location with a program so that it can hold a specified data item value. Similarly, the address can be used by the algorithmic parts of the program to alter the sequence of execution of operations. Instructions are stored in the memory in sequence. When we say sequence, one after the other. Instructions are stored in sequence, like we said. That is, first location will come before the next one. As we go on, we see whether these instructions are accessed sequentially or possible to, access anyone you want at a time. Before we finish the lecture, we'll be able to see that. In order to process these instructions, it is necessary that both the data and the instructions be stored in the memory of the computer. You can see why it's very necessary to know much about the memory systems. Now, let's quickly look at the building blocks. Every memory is constructed from a collection of memory cells, with each having its unique name known as its address. Each of the memory cells contains a piece of data referred to as its content. Every memory cell holds one piece of data at a time. Figure 1 will show us the normal structure of a unit of memory, which is constructed from a number of cells. Each collection of cells has associated with it two types of registers in the central processing unit, the CPU, known as the memory address register, otherwise called the MAR, and the memory buffer register, otherwise known as the MBR. The address of the particular cell to be processed is placed in the memory address register, MAR, and decoded by the decoder to activate the correct memory cell in order that it may be processed. This particular sentence, before we finish this lecture, we will perform it, practically, so that you see what happens, how each address is used in locating a particular memory to access. Because any of these cells can be accessed at random, the type of memory that can do that is called the random access memory, RAM, which we have treated in our module 14. We may not go into it or describing what it is. But a memory cell can be read. That is, the contents of the memory cell are placed in the memory buffer register, or it can be written into by placing the data value in the memory buffer register. During the read operation, the contents of a memory cell remain unaltered, while during the write operation, the cell content is replaced by the value in the MBR, and any data previously stored in the cell is destroyed. So this is our figure 1. So you see, a unit of the memory, we have what we call the memory cells. It can be any number. As we go further, we will see this address numbering, what it is all about. It's a very interesting phenomenon to study how the computer read the addresses. So you see that the MAR will read from the address line, and the MBR will read into the data line. Remember, earlier we have described the memory box, that all the connecting lines within the computer are known as the bus. So we have the address bus, the data bus, and the control bus. But for now, we have not introduced the control bus. We are only talking about the memory address register and buffer address register and how they are connected to the bus. So up there, you see each of those lines are called the memory cell. So in general, every memory system requires several different types of inputs and output lines to perform the following functions. 1, select either a read or a write operation to be performed. 2, select the address in the memory that is being accessed for a read or write operations. 3, supply the input data to be stored in the memory during a write operation. And 4, hold the output data coming from the memory during a read operation. As we go on, these actions, 4 of them, we will see how each one is being performed in real life. So the enable or disable the memory so that it will or will not respond to address input and read-write command. Fig 2, we will see, illustrates these basic functions for a typical 32 by 4. So 32 times 4, 32 by 4 memory system. Now, the memory system is numbered like this. This by this, that by that. We say this example of 32 by 4 memory system simply means that it's a memory system that stores 32 4 bits. That is, it has 32 locations, and each location stores data of 4 bits. In our previous lectures, we have called any 4 bits as a neighbor. So in other words, this is a memory that stores a neighbor, that is 4 bits, into 32 places. Now, because the word length is 4 bits, we had also defined word length. Any number of bits that is used to represent information or data in a computer system is called the word length of that computer. So for a 32 by 4 means 32 locations and 4-bit word. So the word length is 4 bits. So say because the word length is 4 bits, there are 4 data lines: I0, 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 I1, I2, I3, and the 4 data output lines: O0, O1, O2, O3. During a write operation, the data to be stored into the memory must be applied to the data input lines. And during the read operation, the data being read from the memory appears at the data output lines as shown in Fig 3. Now, in Fig 2, we said is the block diagram of a typical 32 by 4 memory chip. And B is the visual arrangement of cells into 32 4-bit words. Now, let's look at the figure on the left, Fig A. The memory, if you look at up, you see the output, which we have described, 00 to 03. The 00 is the least significant bit, and the 03 is the most significant bit. When we did computer numbering systems in Module 19, we showed clearly that this is, powers of 2. So Q0 is 2 raised to power 0, which is 1. Q1, 01 is 2 raised to power 1, which is 2. 02 is 2 raised to power 2, which is 4. And 03 is 2 raised to power 3, which is 8. So you see, when we talked of the numbering system, we talked of the 8421 binary coded decimal. You will see where it is now coming into play. Now, to the left side of it, we see address lines from down A0, A1, A2, A3, A4, meaning that that address is a 5-bit address. And down we see input, which is I0 to I3. Remember, we always put the I0 on the right to represent the least significant bit, which is 2 raised to power 0. Now, if we come to second, the fig B, you see the number 01 number we put in black lettering. If you look at that, it is the address location which we said that this memory chip has 32 address locations. So for us to get up to 32, we need 5 bits. So you see, the first black bit on top is 00000. That is 5 zeros. 4 zeros will have stopped us at 15, at 16. So for us to cross 15 or 16, we have to now have 5 bits. So if we continue down to 11111, that's, if you convert, we give you 31, meaning that for this memory, which is 32 bits, will be from 00000 to 11111. You can convince yourself that 11111 is equivalent to 31. So if you include the 0 location, it becomes 32. So now, in each of the location, for instance, in location 00000, the 4-bit data word stored in it is 1100. So for the next one, which is 00001, the 4 bits stored in it is 1010. Now, as we go on, we will see how this data can be read or can be pushed back to the memory. So we see this last one, which is location 11111. We can represent it in hexadecimal numbers, because if the address location start getting lengthy, it becomes difficult for you to continue to call 111111111. So you change them to hex number. So this last one here, which is 11111, can easily be changed to its hexadecimal equivalent by grouping in 4s, starting from the right-hand side, which is the least significant figure or bit. If you group them in 4s, you see that you have the first 1111 4 ones from the right, and we know that 1111 in hexadecimal is equivalent to F. Then the remaining one will mean that that first one will be 1F. That is equal to 31. So it is as easy and straightforward like that. Please go on. So using this fig 2 as a reference point, the memory under consideration has 32 different storage locations, and therefore 32 different binary addresses ranging from 00000 to 11111, or in decimal you say 0 to 31. Because 0 is inclusive, it becomes 32 locations. Therefore, there are 5 address inputs, meaning from A0 to A4. To access one of the memory locations for a read or a write operations, the 5-bit address code for that particular location is placed to the address input. Fig 2A, like we have seen, represents an arrangement of the 32 registers with each register holding a 4-bit word as illustrated in Fig 2B. So we talked of this Fig 3. Here, each address location contains 4 memory cells that hold ones and zeros that make up the data word stored at that location. For example, the data 1001 is stored at address location 00000. Let's go back a bit to see it. Okay. So that is, see, it may not really tarry there, but see, address location 00000, we have 1100 stored there, just down like that. We will quickly see another example. So, for example, okay, we say that the data 0111 is also stored in address location 00011 and so on. So, but this is a typical addressing system, or how the memory chips relate with the central processing unit. If you look at the line in yellow, we call it the address bus. This address bus is unidirectional. That is, it goes in one direction from the CPU to the memory chips. The data bus is bidirectional because the CPU can write data into the memory chip. It can also read data from the memory chip. That is why the arrow from the data bus from the CPU to the memory chips are bidirectional arrows. It can read and it can write. And of course, the one on red is the control bus. The CPU only sends control signals to the memory chips. So it is unidirectional. Now, if you look at those lines, you see black slash. That slash shows that this is not a single line, but multiple lines. So if you want to indicate the number of lines, when you put that slash, which is a convention to show that it is not a single line, but multiple lines, you can put the number to show the number of, but if you didn't, the fact that you have put that slash, which is a convention, shows that that is not a single line, but a multiple line. Now, note, if you recall in the previous lectures, model 017, 019, we mentioned that these address locations are represented in hexadecimal. Therefore, in Fig B, instead of using strings of binary ones and zeros, their hexadecimal equivalent are used. We have said that. For example, address location 11111 will be written as 1F, because if you start from the least significant bits and group them in fours, the first four represent F in hexadecimal, then the other one is 1. You pad it with 0, which still makes it 1. So it becomes 1F. Now, the read and write in that Fig 2B. Let's quickly look at Fig 2B to get something there. The read and write on the right-hand side, you see R/W bar. The meaning of that is that That terminal is enabled when a high or a 1 bit comes to it. And when a 0 bit comes to it, it becomes a write. So it reads when a 1 bit comes to that input and writes when a 0 bit comes to that. Also, we have what we call the ME, which is memory enable. So say at times it may be, necessary for you to disable the memory. So you use the memory enable. If you make it high, it becomes enabled. You can decide to disable it. So we quickly say that the read write, please note the bar on top of the write. The read write input controls which memory operation is to take place. R stands for read and W stands for write operation. It is labeled R slash bar W input. There is no bar over R, which indicates that the read operation occurs when R slash W bar is equal to 1. We've explained that. The bar over the W indicates that the write operation takes place when R slash W bar is equal to 0. I hope this is clear. So when that terminal is 1, it becomes a read. When it is 0, it becomes a write. Other notations are also acceptable, like in some systems, you just use W bar or WE bar for write and write enable, where W bar indicates that the write operation occurs when the input is low, that is 0, and the read automatically occurs when the input is high, that is 1. Some memory systems have means of completely disabling all parts so that it will not respond to the other inputs. In some designs, it can come as chip select. Some we call it chip enable, whatever acceptable name. So it is usually an active high input that enables the memory to operate always. However, a low on this input disables the memory so that it will not respond to the address and read-write inputs. Memory enable is useful when several models are combined to form a larger memory. For instance, in our Fig 3, you see what we call memory chip 1, memory chip 2, memory chip 3. You can continue like that down to several hundreds of memory chips. So, in talking about computer memories, a concept is very important. We are not going to go into the history of this concept, but a man known as von Neumann has since developed a memory architecture which is known as von Neumann memory organization. And most computers we use today, relied on that initial concept. There are changes now, but we will see. Many computing machines relied on that concept to, develop. So we say a large part of von Neumann concept was concerned with the development of a memory which could be used to store the instructions and data of a program. It was premised on the idea of a linear array of memory cells that could be used to store both the instructions and the algorithms and the data at the same time. Hence, concept is called stored program concept. That is, instead of feeding instructions one after a time, the instructions in form of a program is stored in the memory of the system, and the computer makes use of that stored program to, execute. Of course, it makes the computer to be faster. So that concept is called the stored program concept. So it's synonymous with von Neumann. So anytime you hear von Neumann, you will have your mind rush to stored program concept. The essential characteristics of the computer that employ this type of architecture are: one, they use a single general purpose processor. They use stored programs. They process instructions sequentially, and they can alternate between instruction and execution cycles. However, computers designed around these basic concepts are always known as von Neumann computer architecture machines. Until recently, computers used for information processing were all von Neumann machines. However, the concept was found to have some deficiencies. After many times of use, it was found that this concept have some deficiencies. Two of them are notable. One, only one location of memory could be accessed at a time. Two, there was no physical separation between instructions and data. Therefore, the increases in speed and processing power that we witness today in computing and computing memory technologies were primarily as a result of improvements in the design and construction of MEMS, or what you call the micro electromechanical systems, improvements in microelectronics, and improvements in embedded systems, and not necessarily in von Neumann architecture. Like I said earlier, this von Neumann architecture, or the stored program concept, was like something that came and gave a quantum leap in the speed of computing. But as time went by, we saw that there are deficiencies. One of the deficiencies is that this stored program concept does work sequentially. Because it does work sequentially, if you now have two things to do, you want to add 2 plus 3, and 2 is in another register, 3 is in another register. The system will find it difficult because it has to do one at a time. The second one was that it can confuse data with instruction. And when it does that, because the data is in binary bits, the instruction is in binary bits, immediately it confuses data bits with address bits. It can take data as address and now go to a different place to execute a different instruction altogether. So we say there are two notable deficiencies of von Neumann architecture. So from the two notable deficiencies of von Neumann concept, it can be seen that in the case of the addition of two or more numbers, the computer needs access to two or more registers concurrently, which is not possible. And because there was no distinction between data and instructions, disastrous consequences could result from the system trying to obey or use data as instruction. So, one very important aspect is how these memory chips or memory system of computer interact with the central processing unit. So we say the main memory is in constant communication with the CPU. And as noted in earlier lectures, a computer memory is made up of RAM and ROM. When we say RAM, random access memory, and ROM, read-only memory, that are interfaced to the CPU over three groups of signal lines called buses, as we have seen in Fig 3. The three signal lines are known as the address lines, data lines, and control lines. Each of these lines or buses, but permit me from now on, we call them buses because the real term used in computing is, calling them buses instead of lines. But we can use two of them interchangeably, so you understand. Each of these buses consists of several lines and is therefore represented by a single line with a slash as a convention. The CPU will also store, that is, write data into the memory locations as dictated by the program instructions. Whenever the CPU wants to write data to a particular memory location, the following must occur. 1. The CPU supplies the binary address of the memory location where the data are to be used and places this address on the address bus. The CPU places the data to be stored on the data bus. The CPU activates the appropriate control signal lines for the memory write operation. The memory decoder decodes the binary address to determine which location is being selected for the store operation. The data on the data bus are transferred to the selected memory location. For the read operation, the CPU must also perform the following processes. 1, the CPU supplies the binary address of the memory location from which data are to be retrieved. It places this address on the address bus. It activates the appropriate control signal for the memory read operation. The memory decoder decodes the binary address to determine which location is being selected for the read operation. The memory decoder places data from the selected memory location on the data bus from which they are transferred to the CPU. With the steps above, the functions of each of the system buses can become clearer. 1, the address bus, say that this is unidirectional bus that carries the binary address outputs from the CPU to the memory chip to select one memory location at a time. We will do example immediately after this. 2, data bus, and say the data bus is a bidirectional bus that carries data between the CPU and the memory. That is, it can read and it can write. And the control bus carries the control signals such as the read-write signal, memory enable signal, clock signal, and so on from the CPU to the memory chips. So remember, we said memory are of two types. The read-only memories hold data that either are permanently or will not change frequently. Under normal operations, no new data can be written into a ROM because it's read-only, but data can be read from the ROM. For some ROMs, the data that are stored must be built in during the manufacturing process, which is termed firmware. We have mentioned that in earlier lectures. And for some, the data can be entered electronically, which we call PROM, or programmable read-only memory. There are classes of this PROM, which we have talked in the past. There is no need repeating them here. Some ROMs cannot have their data changed once they have been programmed, but some can be erased and reprogrammed. So we call them erasable programmable read-only memory, EEPROM. So ROMs are said to be non-volatile because data stored in them are not lost when electrical power is turned off. But usually a little CMOS battery, when we say CMOS, complementary metallic oxide semiconductor battery, helps them to retain electrical power for a very long time. And that is why you can keep your computer for so many years before the memory will fail, because this CMOS battery helps to retain power to it for a very long time. The internal architecture of a typical ROM chip is as shown in Fig 4, which is a 16 by 8 ROM. Remember, we've seen 32 by 4. Now we are saying that this one is 16 by 8. The meaning is that it has 16 locations, and each location holds 8 bits of information. 8 bits of information is 1 byte. So we can say 16 by 1 byte ROM, 16 by 8 bits ROM. That is, this ROM has 16 locations, and each location carries 8-bit data. The architecture consists of 4 basic parts: the registers, the row decoder, the column decoder, and the buffer. Now, the register array stores the data that have been programmed into the ROM. Each register contains several memory cells equal to the word length. In this our case, 8 bits, which we see in Fig 4. The registers are normally arranged in a square matrix. The data outputs of each register are connected to an internal data bus that runs through the entire circuit. Each register has 2 enable inputs, and both must be high for data to be placed on the data bus. Now, keep everything you are doing and follow me to look at this diagram. If you look at the diagram, you see the small blocks in blue. We call them registers. To the left, we have the block in orange, which we call 1 of 4 decoder. The one up we call row select. The one down we call column select. Then down we have the output buffer. Then in the diagram, we have lines in black, we have lines in red, and we have lines in yellow. So the registers are numbered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. In other words, from 0 to 15 is 16. So you can see what we mean by 16 by 8 means that each of these registers holds 8 bits of information, means that each of these register has 8 word length. That's the word length of what we are considering is 8 bits. So you want to get data from register 0. When you want to do that, you have to activate the enable of that register 0. The enable there are two, one on the left, one on the right. The one on the right has the red line as input, and the one on the left has a black line as the input. Now, when a system, your design, wants to select that register 0 to either read or write to it, it will place 0, 0 in the address input of the upper 1 of 4 decoder. When it places 0, 0, a 0 bit, the 0 line is enabled. And that 0 line, which is the black line, will come out, will be activated, and the enable input, the E, the black line of that register 0, will become active high, which is 1. At the same time, it will place in column select, that is A2, A3, it will place 0, 0 there. When it places 0, 0 there, the 0 output line will be selected. So the red line, which comes out from 0 and goes up to that register 0, will be the only one that has the active 1 input. So the second enable input will also be high. So you see that the enable input from the black line is high, and that from the red line is high. So that register 0 will be the only register that is active, that is enabled in this diagram or this memory setup. Then the content of that register will be placed on the yellow line, which is the bus, and that bus, that data will follow the bus and come down to the output buffer. Now, if a chip select is 0, then the output buffer will be, activated, and the data will go out, which is 8-bit data will go out from the D lines, which we see from the right to the left, D0 to D7, that is 8-bit. Now, let's look to the right. We are seeing to the right a table that has A0, A1. That is how that 1 of 4 decoder works. When we say 1 of 4, there are 4 outputs. At any point in time, only one of those outputs will be active. So if you put 0, 0, the 0 output will be active. 0, 1, the 1 output will be active. 1, 0, the 2 outputs will be active. 1, 1, the 3 output line will be active. If you come to the column select, the same table holds. So you see that when you have 2 inputs to a decoder, you will have 1 of 4 decoder, you have 4 outputs. So different decoders are bound. You have 1 of 8, you have 1 of 16, you have 1 of 32, and so on. But let's quickly, convince ourselves that we know what we are doing. If you look at that table, we had 2 decoders. So each has 2 inputs and it has 4 outputs. The meaning is that if we have 3 inputs, we will have 3 by 3 of 1 of 8 decoders. In other words, you will be able to address 64 registers or 64 memory locations. Remember, this example we did, we have 2 decoders. Row select has 2 inputs. Column select has 2 inputs. So we're able to address 16 locations. We are now saying that if we have 3 inputs in the row and 3 inputs in the column, we'll be able to have 64 registers, because 3 inputs will give you maximum combination of 111, which is 7, plus the 0 location, making it 8. So you'll be able to have 1 of 8 decoder. So 8 by 8, like we have in that one, the first one, 2 by 2, which is 1 of 4 decoder, we have 16 registers. 3 by 3 will give us 64 registers. 4 by 4 will give us 256 registers. So we've given example table here of four inputs, A0 to A4 address lines. So if you have it, it will give you 0 to 15, which is 16. So if you have it as row and have another one as the column, you'll be able to select 16 times 16, which is 256 registers, which is the same thing as memory locations. If you have 5 bits or address bits, you'll be able to have 5 by 5, which will give you 1 out of 32 decoder. And that will give you 1024 registers. So when you make use of 5 bits, your system will have 1K memory. So if you have a system that is, rated 1K memory, it means that it's making use of 5 bits. That is address lines A0 to A4, 5 bits. So if we now continue and you hear that this system you are holding, this your phone, this your computer, is a 16-bit computer. In other words, the address is from A0 to A15. You can now, use this similar thing to see that what will be the number of locations? You see that the number of locations will be many, and your memory capacity of your system will now be going in several kilo locations. Now, you imagine when it is 32 bit. You imagine when it is 64 bit. That is why if you go to buy a computer, they will tell you that this is a 64-bit computer. This is a 128-bit computer. And each time the memory jumps so high by just a small difference in number. Look at this. From 2 by 2 gives you only 16 registers or locations. 5 by 5 is already giving you 1K, 1024 locations. So that is how you rate or know how the size of memory, which they tell you when you go to buy, any digital system come about. So let's quickly paraphrase what we said. The applied address code represented by A3 as the most significant bit and A0 as the least significant bit determines which register in the array that will be enabled to place its content onto the bus. Address bits A1, A0 are fed to a 1 of 4 decoder. Please, in our next lecture, we will start looking at, these hardwares and see how they really operate, the internal constructions of them that enable them to select 1 out of 4. So address bits A1, A0 are fed to the 1 of 4 decoder that activates 1 row select line, and address bits A3, A2 are fed to the second 1 of 4 decoder that activates 1 column select line. With this, only 1 register will be in both the row and the column selected by the address inputs, and therefore will be enabled. For example, in that fig 4, if address input is 1101, it means that A3, A2 is equal to 11, and this will cause the column decoder to activate column 3, while A1, A0 is equal to 01. Remember, the least significant bit will cause the row decoder to activate row 1 select line. This will place highs at both enable inputs of register 13. I want you to confirm that, thereby causing its data output to be placed on the bus. Similarly, if we want to read data stored in register 7, we will now look at that diagram and we will see that it is row 3 that will be activated and column 1 that will be activated for register 7 to be active. So if we look at that, what will we place as input A0, A1 to activate row 3? From the truth table we have there, it means that we must place a 1, 1, which is equivalent to 3 in decimal, to activate row 3. And in the column, which is A3, A2, we must place a 0, 1. 0, 1 is the same thing as 1, and that will activate column 1. So where column 1 and row 3 intersect is register 7. and the memory, store, or the data stored in memory location 7 will, be read. So as we go on, we will also look at these registers, because registers, like we say in this one, hold number of bits. These bits at times may be read one in, one in, one in. So we will look at registers and see how they are being read. It could be first in, last out. It could be last in, first out, all those. So it's part of things we'll be looking at in future. So we say, thus the required address will be from A0 on the right to MSB L3 will be 0111. So buffers, like in that diagram, we saw a buffer. The register that is enabled by the address decoders will place its data on the data bus. This data is temporarily stored in the output buffer before giving it out to the external device, provided the chip select is low. That is why in that figure, the chip select has a bar on top of it. So at this time, we want to refer you to my earlier lectures so that you read the ROM types. There are so many types of ROM. Read about them. They are not, things that are difficult to get by. So we have the other type of memory, which we call the random access memory. So say RAM is used to describe the type of memory used for temporary storage of programs and data in computers. A major disadvantage of RAM is that it is volatile. That is, it will lose all stored information if power is turned off. However, the main advantage of RAM is that it can be written into and read from rapidly with ease. Also, with RAM, any memory address location is as easily accessible as any other one. It is important to know that the size of RAM determines the capacity of the computer, because it holds the program that is being executed by the computer. If the size of the program is bigger than the RAM size, that computer cannot execute that program. We will stop here today. Thank you for listening, while we hope that you will join us in the next lectures, when we will start looking at the Boolean algebra, the mathematical formula that led to the development of all these memory chips that we are talking about. Now we have seen how memory works. Again, we mentioned MEMS, micro electromechanical devices, which was able to integrate all these chips so that we can be talking of 1 gig of memories. Now, we have seen what just 16 memory locations, what it took to get it, and just the small difference that gave 1 kilo. So please join in the next lecture, probably by next week, so that you get and follow the pattern. Thank you for listening. Please share and make your comments. I'll be able to answer them. Thank you.